to learn more about the thermal resistance that you have seen it in building science. But here, this chapter is focusing only on a steady state scenario. It means we have no energy storage capability. Therefore, this is the part we're going to solve. And also, we're going to extend these cases for some scenario like cylindrical coordinate, how to solve that problem. In some cases, in case of wall, we mentioned if we increase the thickness of the wall, if we increase the resistance, we can reduce the energy losses to the wall. But probably that's not the solution for other scenario like cylindrical. Therefore, and we were trying to see why it has a certain limit. And then we're trying to apply in the case of some application that we would like not decrease the heat transfer, we would like to increase the heat transfer. And that's the case of, for example, your computer, because you generate a lot of heat and you would like to release that heat in order that the sensor that work properly, okay? Therefore, that's some of the problem we're trying to look at this chapter. If you look at Fourier transfer equation that we have here is Fourier law of conduction. If you look at the wall, we have it very easy. We have Q equal K dt over the A. In this case, A is the section of area. Okay, K is conductivity, and this is steady state. Therefore, this Q become constant. Okay, therefore dt over dx is constant, and you have seen it in some problem that is a slope is constant all the way. Okay, therefore, if we assume this dt over dx is constant, we can change it to this integral equation by that time difference, that Q wall is equal Ka T1 minus T2 over L, okay? This is a linear, therefore, but we can easily change that the slope to the difference, and that becomes T1 over T2 or L. And that's the one we did it again in building science. And then we try to come up using the analogy. We're using exactly, we did it in electrical engineering, that yes, we have a voltage difference and there's a resistance. The current passed through the resistance is proportional to the voltage difference. Now we have, in this case, we have a heat transfer passing through a wall, and the difference here is potential difference is T1 minus 2. And therefore we were able, from equating this equation, what we had it before, find that this is resistance, thermal resistance in the case of the wall. Therefore we define thermal resistance is equal K L divided by K over R. And you can see if you increase the thickness in the case of wall, your resistance will increase. It means less heat pass through the wall, okay? Therefore, this was the definition that we had. Similarly, we define also resistance related to the convection, okay? Therefore, we did it, we applied in building science. Now look at in the case of cylindrical coordinate. The cylindrical coordinate, again, we can apply the Fourier equation, okay? The Fourier equation, again, is become Q is equal conduction. This is only, we're talking about passing heat transfer to the solid material, equal K, and we have to define what is A. A is the cross-section area of the pipe. It means 2 pi R times L, and dt over dr, and that's the temperature difference across the solid material that we have. In order to apply this equation, again, we have to make an assumption that the two surfaces of the cylinder are maintained at a constant temperature, okay? Therefore, this is a steady state. Therefore, the T1 inside the wall and T2, this is T1 here and T2 are constant. Therefore, we are talking about steady state, okay? And again, we assume no heat generation. That's again another assumption, there is no heat generation. And we assume the thermal conductivity is constant. And again, it's assumed it's one-dimensional. Therefore, if you go back with the equation that we got in the last chapter, the big equation that if you make those assumptions, you will end up that yes, Q is equal K A dt over dr. We assume T1 here, we assume T2 here, we assume the thickness is the difference between these two, and the rest here is conductivity and everything is constant. Therefore, if we assume this delta T is constant, therefore the heat transfers become constant here, okay? Therefore, we assume it's a steady state. It does not change as a function of the time. If we go one step further, we can write down the equation here is K over this one. We assume that R equal R1, T is equal T1, and R equal R2, T equal T2. Therefore, if we integrate from both sides, again, remember this is a differential equation that we have here. Therefore, this can be transferred to this equation. Simply, why this happened here is we did it as part of the problem last lecture because A is equal to 2 pi RL here, okay? We place it here and integrate from both sides, we can find that this is become your conduction to the cylinder. Conduction to the cylinder is still the temperature difference that you have here, is still that you have a K here, but because of the geometry and integration from both sides, we end up with this term, okay? Therefore, now we can simplify this equation as we had it before to T1 minus T2. And we're trying to define what is the resistance. The resistance is the remaining portion that you have here. The resistance is the remaining portion. Now, we have resistance is equal to this one. L and R2 over R1 divided by 2pk. Therefore, now we have been able also to define an equivalent resistance in cylindrical coordinate, okay? Therefore, keep in mind, when you're dealing with the cylindrical coordinate, resistance is absolutely different from the solid, from the wall, okay? Therefore, now we can go back and use the same analogy that we had. For example, if I look at this scenario that I have a fluid passing through the pipe, and the temperature is T infinity, and outside is T infinity here. Therefore, I have convection here because the fluid is passing, you have a convection, and you have a solid material, you have a conduction, and you have here is convection. We already know how to define these two convection. This is heat transfer coefficient H1, and this heat transfer coefficient H2. But keep in mind, please, that area here is referring to area of this part. Therefore, we are dealing with this radius here. And when I'm dealing with area on the other side, I'm dealing with area R2. Therefore, keep in mind, when you're defining resistance here, is convection. This is area that the fluid is in contact with interior surface. 2 pi R1L. If you're dealing with outside, the area is changing, become 2 pi R2L, because the outside convection is dealing with this surface outside that you are dealing, okay? And for inside, I'm dealing with these surfaces here, okay? And for keep in mind, this is the scenario we are dealing. And now come back to the solid here, heat transfer resistance here, as we define here is the ratio of these two resistance divided by K. Any question, please?
Sir, can you please go back to the other slide?
Say it again.
Can you please go back to the other slide? The previous one.
Yes, sir. Look at that. If you have any question, ask, please.
Good, thank you.
What happened again? Let me go back to see what. Okay. Therefore, now we define resistance here, and now we are trying to look at every problem that dealing. Again, we use the same analogy that we used for the wall. Okay. For the wall, it was easy. It was X over K. Okay. But now we are dealing with the cylindrical coordinate, and the exposure area to convection is changing from inside here that you are dealing with this radius to the outside that you are dealing with also. Therefore, please keep track of the area that you are dealing, okay? Therefore, you can see it's changing, okay? Any question, please? Therefore, now I'll calculate the total, and then become the total heat transfer is the temperature difference between inside and outside divided by the total resistance. Okay. Again, if we have multi-layer, the same thing that we did for the wall. If I have several layers of insulation and so on, therefore I have convective inside and depend on the thickness of this one. Therefore, the radius will change from R1 to R2 for the first layer, R3 to second, and R4 here. Therefore, I have to keep track of all the changes in the cross-section area. You have convective heat transfer for inside, convective heat transfer outside. The rest is a solid material. The rest are solid material, and you have to remember what was the resistance for each of them. Okay. And for spherical, again, we are the same thing. We can apply it for spherical. We have to extend the equation. Okay. For these are equations that we are dealing with. It is for cylindrical, R2 over R1, R3 to R2, R4. But also here is conductivity of the material 1, conductivity of material 2, conductivity of material 3. Okay. Any question? Good. Now I do have a question. This is a problem is your textbook, I believe it's 381. If you have your textbook, please open it and try to do it and let me know what is the answer. Therefore, we have a steam passing through the pipe. The temperature of the steam, T1 infinity, we call it, if you like, is 280. And this is stainless pipe. The conductivity is around 15 watt per meter per degree. And since it's a pipe, it has a thickness. The inside diameter is 5, the outside diameter is 5.5 centimeter. Okay, therefore it is 5 centimeter, and the other one is 5.5 centimeter. We put the cover with a 3 centimeter thick of insulation, and that's the conductivity of the insulation. Heat is lost to the surrounding at 5 degrees. Therefore, now the insulation outside is exposed to an environment that the temperature is 5 degrees by natural convection. With a combined convective and radiative heat transfer coefficient 22. Therefore, from outside the insulation to the environment, to room air, to outside, the convective heat transfer is 22. Okay, therefore this is H2 infinity. This is outside. Taking heat transfer inside the pipe. Therefore, if we assume the pipe, the fluid is passing, the steam is passing through the pipe, create an environment that convective heat transfer is 80 watt per square meter here. I would like to find out how much is the loss from the steam per unit length of pipe. Okay, therefore L we assume here is 1 meter. Okay, and also we would like to calculate the temperature drop across the pipe shell and also across insulation. Okay, I gave you a few minutes. Try to do it a step by step, and to see how far we can go. Therefore, you have all the information. Therefore, you have the best thing here first, draw the thermal network of the problem. Therefore, you have 4 sections. Inside, you have resistance to the convective heat transfer inside the pipe. You have conduction through the wall, and then you have conduction through the insulation, and from insulation to outside. Okay, therefore you have 4 resistance. For outside and inside the pipe, we can clearly define the resistance is 1/2 pi R L H1, 1/2 pi R H2. Okay. Therefore, if you look at here, to solve any problem, we make a certain number of assumptions. First, assume is a steady state because no indication of any change with the time, because we mentioned these two temperatures constant. That's now make it this is a steady state scenario. And is assume is only one dimensional. We assume because the pipe is too long, we can assume there is one line. Okay, and we assume the temperature is almost constant inside and outside. The thermal conductivity of material is given for stainless steel and insulation is given to you. And we assume the resistance, there is a close contact between the insulation and the pipe. Therefore, there is no air gap in between. Okay, this is a complete contact between these two. Making this assumption, you can come up with this resistance that I have here. Fluid is passing through the pipe. There's a resistance between this and to the surface of the pipe here. Write T1, please. Here, write T1. And then you have to the pipe material, stainless steel. It has a thickness of 0.5 centimeter. You can put this one as T2, okay? And then from here to the insulation, and you can put this one T3. Therefore, you have resistance to the convective heat transfer inside the pipe, convective heat transfer, conduction to the wall, conduction to the insulation, and convectivity. Yes, sir.
Can you go back a few slides? I just want to see the diagram where it cuts the circle in different layers.
I will cut it for you right here. This is the conduction. This is you're cutting here. You put a pipe.
No. I just want to see the diagram.
This one?
No. Oh, wait. I have to wait. Maybe there's a delay. Okay, yes, this one.
This one?
Okay, so the R is always from the center of the...
That's the definition of the radius.
That's fine. That's fine. Thank you.
For now, we have resistance. This is R is not radius. This R is resistance. This is capital R. It means resistance. Okay. And this is resistance. Again, is capital R is resistance. This is capital R resistance to the conduction to the insulation. And this is resistance to the convective outside the pipe. Okay. Now we have to go and calculate each of them. Now let's go back. This is defined as 1. We are dealing with heat transfer through the fluid to the pipe. Therefore, the area of conduction, the transfer to the fluid here is, this is the part of dealing here is this interior surface of the pipe. This interior surface of the pipe, therefore, the contact area is 2 pi R L times this, okay? So that's here. Okay, please do the rest and I will. Before we're going to calculate here, the interior pipe here is 2 pi R or D. D is equal to pi. Therefore, we know the radius of inside. We assume the length is 1. And this is become the surface area for inside. This is the surface area for inside this one, okay? And then the outside surface area is dealing with thickness of the pipe plus thickness of the insulation. Therefore, that you can see this is the thickness of the radius, the diameter of the pipe, exterior, outside, and here is the thickness of the insulation. Therefore, this is representing the insulation in contact with outdoor environment. Therefore, this again is D0, is thickness, the radius of the pipe plus the thickness of insulation, okay? Therefore, that's Y.6, if we are wondering why here, because here we mentioned 3 centimeter, and if you look at the both sides of the pipe, therefore that's become 6, okay? If that was 3 centimeter, that's 3 centimeter this side and 3 centimeter this side, for the diameter here become diameter of the pipe plus twice the thickness of insulation, 0.3 centimeter here, 3 centimeter here. This gave you that one here. We go back and calculate. First, we're trying to calculate the convective heat transfer for inside. Therefore, that's become HI times AI. Therefore, this is the area that fluid is in contact with interior surface of the pipe. We have H, we have the surface area, we can calculate. Let me go to the outside. I have for outside to the environment. This was a convective heat transfer. I'm sorry, here, outside, okay? Again, we mentioned this a combine of convective and radiative to give them also one number to make our life easier. And here is the surface area, okay? Therefore, we calculate for Ri and Ro. But in between, we have 2 layers. One layer we have for pipe, and one layer we have for insulation. Therefore, here we're trying to calculate the 2 parts that we have. The definition of conduction through the wall is equal R2 over R1. And this is the conductivity of the pipe. Therefore, this is the definition of resistance for cylindrical coordinate. 2.5 point is 2.5 here is. Again, this is half of this representing exterior diameter, and here in the inside diameter, outside and inside, okay? Therefore, that's there is half of this and half of that, because we can put also 5 and 0.5, it doesn't matter because both of them is divided by 2. Again, we put it in centimeter for the simple reason because both of them is divided by 100. Again, it's the same, okay? And therefore, make sure that to understand where this 2.75 came and 2.5 came, okay? 2.5 is 5 centimeter divided by 2, 2.75 is this one. I put R in order to make it. You can put D, it's the same because both of them can be divided by 2. Again, here is a conductivity, and here we assume the pipe length is 1 meter. Therefore, we calculate. The same thing, we calculate the resistance for insulation, okay? For insulation, that we have a layer of insulation, we mentioned is 3 centimeter, okay? Again, here is, we have 575 and 275. Simply remember what it is. This is relating to the thickness of the radius of pipe, and here is the radius plus insulation, okay? Therefore, keep in mind, these are the numbers. This is the value of K is given to us, and here R is in here. Therefore, now we have been able to, yes, sir.
For the ratio R2 or R2 over R1, I don't find the same thing, because I use 2.5 centimeters and 3 centimeters for the outer one.
No, look at here. Your pipe, has a certain thickness.
It's 0.5.
0.5. And then you have, for 0.5 is the thickness here, right?
Yes, plus 2.5 from the original radius.
2.5 is interior, no.
Yes.
This is the radius from inside is 2.5. Okay, is 5 centimeter, right? 5 centimeter divided by 2 become 2.5.
Yeah.
And for exterior here, this one without insulation is 5.5. 5.5 centimeter. 5.5 divided by 2 become 2.75.
Oh, okay, yeah.
That's okay. That's okay. That's okay. Again, as I mentioned, you can put even the diameter because both of them is divided by 2 will cancel out. Okay. If you're comfortable, you can put 5, put this one and this one or this one. Okay. Here, I simplified just to make it easy. Okay. You can divide it. If you put it in meter, both of the meter 100 will cancel out. In this case, you have 2.5 plus 3 centimeter of insulation. 2.75 plus 3 centimeter of insulation give you 5.75. And here is the case of R2 only for the pipe. Therefore, now we have been able to identify each of these resistance. The same as wall, we add them all of them together. For resistance from inside to outside, here is degree over watt, okay? And since we assume per meter, therefore that's here, okay? We assume here is per meter and we assume per meter here, okay? Any question, please? Look at that. If you have any question, and let me know. Therefore, now look at here. Now we have been able to define Ri, convective part, pipe, still, insulation, plus convective to outside, R0, R2, R1, and Ri. Therefore, we know now the resistance, the total resistance from here to here, I will add them up together. Okay, this is the total resistance between inside the pipe because I know the temperature here and I know the temperature here. I will add them up. Any question, please? Please let me know when you're done. Okay, now the problem is asking you the heat loss, okay? Therefore, you know the temperature difference now, inside and outside. You know the temperature inside the pipe, the fluid inside the pipe, the temperature outside. Therefore, you know the temperature T infinity here, and you know what is, calculate the heat loss. Tell me the heat loss. How much is the heat loss? Easily calculated. Q loss is equal to the temperature difference divided by the total resistance.
83.43.
Okay, let me see if you're right, sir. I find this one. Is it what you said?
I said 83.43, same thing.
That's okay. No GST and no PST, right? Now, the second part of the question asking you, what is the temperature across the wall of the pipe? The second part of the question is asking you, what is this temperature? And what is this temperature difference? It's not asking you to find the temperature here or here. He's asking you the temperature here. Go back. He's asking you also calculate temperature drop across the pipe shell and insulation. He's asking you to calculate those two temperature drop, okay? Therefore, we are trying to find this temperature difference, okay? We would like to calculate the temperature difference across the pipe shell and also across the insulation. Could you tell me what is the temperature difference? Temperature drop. Therefore, as we mentioned, steady state, it means the heat transfer from here to here, from this one to here, is equal to heat transfer from here to here, from here to here, from here to here, and from here to here. What that means, from this part, heat transfer is 83.4, 83.4, 83.4, and 83.4. Therefore, the Q, we call Q1 or QI, Q1, Q2, Q0, okay? Therefore, this heat amount is a steady state. It does not change, therefore, to remain the same. I know the resistance here because I calculate R1. Therefore, I can easily calculate the temperature drop across here. 83.4 divided by R1 gave me the temperature drop here. 83.4 divided by value of R2 gave me the temperature drop here. Therefore, that's exactly what happened here is this one, okay? Therefore, across the pipe is equal Q, this one. I know this one, and I know temperature drop, this one here, okay? Therefore, remember, we Q equal this divided by resistance. I know this one. I know this one for each section of here, each section. Therefore, I can calculate the temperature drop. It did not ask me the temperature T1 or T2 and so on. Okay, it did not ask us to calculate the temperature. It only calculate what is the temperature drop. Therefore, I can calculate temperature drop. Now, if I want to calculate the temperature at this point here, I know R1, I know T temperature, I can calculate temperature here. And for the same thing here. Any question, please? As you can see now from this result, the conclusion we make here is, look at here, the resistance was very small. Here, and also here we have a lot of resistance here. You can see the effect of the internal insulation. Any question, please?
All clear so far, sir.
Good, thank you very much. Now let's go back to that what we had before. Let me come back here. Look at here. We mentioned the resistance from here to here is equal to resistance this part from the conduction, convection, and here. Okay? If I look at here, this is my resistance here. R4. R4 is this one. This one related to this R4 that we have. Radius from here to here. Okay? Now this is supposed to be R4, okay? This is my R4. This is wrong here, R4. If you look at this equation that you have, if you increase the thickness insulation, if you increase the thickness of insulation, what will happen to resistance? If I make, rather than 4 centimeter of insulation here, the thickness 4 centimeter. If I make it 10 centimeter insulation, what will happen to this R4?
Is going to increase.
Increase, what will happen? If I increase, what will happen? If I have more area, what will happen? I have more heat transfer. Can you see it? If I increase this one, the area becomes bigger, and a convective heat transfer from my exterior surface is called HA times delta T. Therefore, my area will increase. As the area will increase, my resistance will decrease. My resistance decreases. If I increase this one, the resistance will decrease. This brings us to the subject of This part, okay? This part, okay? If I increase, if I look at my energy equation that I have, my losses from inside to outside is the combination of this resistance plus this resistance. I can have also resistance here, okay? But usually this one is very high, I can ignore it, okay? Okay, therefore my H is very high, become very low resistance. But the main resistance here is insulation and convection outside. But you can also add this one, there's no problem, okay? Just trying to show you the effect here. Look at here, because if you increase your insulation, this one will not change that much, okay? Look at here, you have R2 or R1 here, plus this one. Now, if you increase this R2, your surface area will increase. And therefore, your losses by convection will increase slowly. Therefore, in case of cylindrical coordinate, there is always an optimum value that gives you the best effectiveness, okay? After that, the radius will, increasing the insulation has no value anymore, okay? Therefore, you have to keep in mind how we'll do that, okay? There's a problem that we are going to solve it in assignment, and also if not, I will do it, that we can see there is an optimum, and that optimum depends on that optimum thickness of the insulation is the ratio of conduction of the insulation material to convectivity heat transfer. That's dependent on that one, because that make a balance between the losses that you have from here to there, okay? Therefore, keep in mind, for the case of wall, you can increase insulation, your X will increase, therefore you have higher resistance, okay? It's X over K. If you increase X, the resistance will increase. But in case of cylindrical coordinate, we have to balance between these two, between conduction through the wall that you have to do your insulation, to the convection to the outside, okay? And that's, we give you an optimum value that after that, the insulation, adding an insulation, your losses will increase more and more and more, okay? We do the problem later on that you can see also mathematically how we solve this one. Now, any question? Therefore, again, let me go back. Let me go back again. How we define the value of the thickness of insulation. You can see this is, you have a convection here, the conduction here, and when we define a resistance here, we have to keep in mind there are 2 points we have to remember. The area for convection will change from inside to outside. You have to keep track of that one, R1, R2. And also, when we define, this is the definition of resistance in cylindrical coordinate, okay? We do one problem later on that also show you for the application for a spherical coordinate, okay? Therefore, keep in mind the resistance will change as we change the coordinate from Cartesian to cylindrical to spherical coordinate, okay? As I mentioned, most of the cases in building, we would like to reduce the heat loss from the system, because that's the whole idea. We are using insulation. But in some application, we would like to increase the heat loss, the heat transfer. A simple example in heat exchanger. In heat exchanger, we would like to increase the energy exchange between cold side and hot side. If we increase the area of the heat exchanger, the size will increase, the cost will increase, and then we have a problem with space and cost. In case of we are dealing with a computer, again, we would like to increase the heat loss from the chip, because if the heat accumulate there, the efficiency of your chip will decrease. Therefore, there is need that we intentionally would like to increase the heat loss. We would like to do that. But at the end, when it comes to heat loss, at the end part is the convection part. Your losses to air In the case of heat exchanger, losses to fluid. It either hits cooling side or heating side. But there is again a limit. Again, you have to look at the practical aspect. How you're going to increase your H. The only way we can increase the value of H here is by increasing the velocity. It means you need a bigger pump. You need a bigger compressor. Therefore, if you increase the velocity, your heat transfer will increase. If you don't believe me, go back to your building science. Table 8.3 that mentioned the heat transfer is a function of the velocity, okay? Therefore, you have to use a bigger pump, you have to use a bigger compressor or fan in order to increase the air velocity or fluid velocity, okay? Therefore, there is an associated cost with that. And you're running your building day and night for 365 days, 24 hours a day, okay? Therefore, that's energy used for pump, compressor, and so on. And if you would like to put it in your computer anymore, you don't have any more laptop. Again, you have to go back to old system. You have a fan in the back of your computer. Therefore, we have to be trying to design a system encouraging the heat loss as much as we can to bring the temperature of the system down and down. Okay? Therefore, this is not applicable. We cannot increase this one. And also, if you would like to increase the size of the chip, the size of your computer will increase. If you would like to increase the heat, the contact between the fluid, hot and cold, and heat exchanger, again, the size of your heat exchanger will increase. As the size of heat exchanger will increase, the pressure drop will increase, then you have to beat it up. Therefore, now we are trying to add the surface area, not directly by increasing the size of the heat exchanger, but by adding fin. And you can see it in here in chip that you have in your computer, in your car. Open the hood and look at the water part or radiator part, and also around the fin. This is how we are going to solve this one. Again, therefore, we need sometimes to increase the heat loss, okay? It's not only reduced, but sometimes we do talk about it. As I mentioned, H is not possible because you have to increase the size of the pump or the compressor area. Again, the space, you have a limited space in your mechanical room, in your car, and so on. And here, these are, we call it extended surface or fin. You can see even the light these days, the bubble they added here because they would like to decrease the temperature of the power bulb, okay? Here you can see it, and here you can see it in your car. These are extended surface, or we call it a fin. And here exactly what you can see in any heat exchanger, okay? And if you don't believe me, if you are heating your room with electrical baseboard heater, just bend and look at your electrical baseboard. You can see there are fin all over, okay? The question here is how I'm going to calculate the energy transfer now. Because now, how do I integrate this phenomena to my basic equation of conduction or convection, okay? That's the way we are trying to develop a methodology, a procedure to be able to calculate that energy transfer. Therefore, if I make it simple, this is my fin. Assume this is the base of your radiator. This is the base of your chip in your computer. And if you would like, even in car that you have here, you add some extended surfaces. They call it extended surfaces. In some textbooks, they call it extended surfaces, or they call it fin, okay? The fin, it means this part. Now, we have to, therefore, now heat transfer from your system is not only from the base part, but also to the fin part, okay? Therefore, there are some energy losses from the base that you have, and also from the fin. From the fin the heat transfer comes from fluid, whatever it is, from here to this surface. The temperature here is almost, we assume, is TO, and then slowly pass through this part. Usually the fin are made of very high conductivity material because you would like to encourage, therefore is still copper and so on. Therefore, these are conductive materials that heat transfer from here. As heat transfer through here, there is losses by convective to outside. Therefore, now you're increasing the area without increasing the size of your heat exchanger, okay? Therefore, now increasing the surface area between the hot fluid or cold fluid and in order to increase the losses. Therefore, the rate of conduction into the X here, therefore, what I'm trying to do that, I'm trying to develop a methodology or an equation to be able to calculate how much heat loss from this part of the fin, okay? Remember, it has a top, it has a bottom part, is exposed to heat transfer, to ambient temperature, and also we have a solid material here. There's a solid material is conduction. Therefore, heat transfer here is by convection to outdoor, and also conduction to here. And for the rate of the conduction, if I take a control volume here, I trying to write an energy balance for this control volume. Energy balance for this control volume, I have conduction coming here, that's my conduction, and a conduction leaving this control volume. Again, keep in mind, this is a control volume, a slice of that fin, and I'm using heat loss to environment by convection. If a conduction come at X here, conduction leave from this side here, and I have conduction going this direction, and this is my convection to outside. Again, the same thing that we did it before. This is my equation. Before we write this minus this, again, the same. We can put this minus this equals 0, doesn't matter. What is a convection? As I mentioned, here is through this surface. From the top here, from the side here, from the beneath, and so on. Therefore, is the perimeter of this control volume, the perimeter of this one, that means this plus this plus this plus this times the thickness. And that's exactly the surface area that I'm losing by convection. And again, I do not know the temperature of here, because the temperature, as heat moves to this direction, the temperature will drop. Therefore, here is TO, here is T infinity, and this, my temperature, my T here is something between here and here. This is my unknown. Therefore, here is unknown, I do not know. I have to go. Therefore, if I simplify this equation and the Qx at conduction minus Qx, again, I can use Taylor expansion, simplify this part, and here divided by X by P, and that's become here. This is HP and divided by X, and so on. Therefore, I take the limit of this one and I push X goes to 0, that will change to a differential equation that will end up here. I will end up dq conduction to that control volume. This is HP. H is my heat transfer coefficient, convective heat transfer coefficient. P is, again, I mentioned the perimeter of the system, and here is temperature of that fin at any point losing this one. Do you have any questions so far, please? Do you have any question, please? Okay, let me go back, look at this slide, try to understand, and then I will continue. We take a control volume, and base for that control volume, right, I write an energy balance equation. And since there is no storage, there is no heat generation, is only by conduction, convection. Okay, that's the story here. There is no storage capability, there is no energy generation, is only by conduction to the system and also convection. That's why I end up here. Convection is this one, and we write the conduction here, this because we wrote for control volume, the thickness of delta X, and I move that delta X to become the direction of 0, that become a differential equation here. Again, here is conduction. Again, conduction, I can use the Fourier equation, put this one Fourier equation right there, place it here, this one, therefore rather here become d over dx term of this part. Okay, this is my Q, and for this become transferred to this equation. Again, look at here now, I have a second order differential equation. This ordinary differential equation because it's only function of x. There's no time is not involved. Therefore, now again, I have to make a certain assumption. If I assume k is constant, I can take k out of this part here. If I assume k is not a function of x, I can remove it out. And if I assume this is only a rectangular system, the delta, the cross-section area, this part, you look at here, this AC, this part, is not a function of x. If it's not function of x, I can also remove that part out of that equation, and therefore becomes second order differential equation, and here is a convection. Therefore, here is t unknown, and here I have second order differential equation. I need two boundary conditions to solve this problem. Again, please look at it, check, and if you have any part that needs further explanation, let me know, please.
What does the variable P represent?
Conductivity of this fin. This is I'm selecting because I want to increase my heat loss. Therefore, this is the conductivity of this extension part, okay? Therefore, usually we use metal, high conductivity metal. Therefore, the K is the conductivity of this solid material that I have here.
Thank you.
No problem. Okay?
Sir, in our case, AC is constant, right?
At this case, I will assume its case is constant, okay? In some problem that we are dealing, AC here, all of them is constant. Sometimes they make this one triangle because of the application, because of this, you can see this fin, this part rather than be rectangular, probably sometimes like a triangle, okay? Depend on application, we have different geometry of fins, okay?
Okay, thank you.
And look at here, they have here, this one. Okay, now we'll come back again, something that I'm sure you like it very much. We're trying to solve this differential equation. As I mentioned, it's an ordinary differential equation that we have here. We need two boundary conditions to define, to be able to solve this differential equation. Again, we have to go back to reality to see what type of system that we have, okay? Because there are different solutions to this differential equation, and that depend on the design of the fin, okay? Let me go back again to this one, again explain to you. Look at here. If you look at this one, you can see the fin is too long, right? Therefore, the fin is too long. Therefore, you can make an assumption. The temperature in this part, tip of this fin is the same temperature of the air. That's relatively with good assumption that we can assume that the case. If we assume the fin is too long, we can assume the temperature here is the temperature of the ambient. Therefore, that could be one scenario that I'm trying to solve. If I try to solve this scenario, look at here, this fin is extended. This is almost continuous, okay? Continuous, okay? Therefore, somewhere in between this pipe and this pipe, the temperature is almost becomes symmetric, okay? Therefore, depend on the scenario that we are trying to solve, we can have different assumption. Therefore, in this scenario of fin that we have a second order differential equation. We need to solve it, and we have to see what type of fin that we have. And based on that type of the fin, we can make a boundary condition, because we need two boundary conditions. Let's see how we can solve this one. First, we have to simplify it. Therefore, I can change this differential equation to look at here. The second order, I can assume K is constant, take it out. I can AC is constant, I can take it out. Become second order of this one. And then become like this. By change of the variable, I'm sure you remember mathematics that you have. Therefore, now this becomes second order differential equation is the same as before. The only thing theta is defined as this one, and M is defined as HP over KSC. This is comes from simply dividing both sides by this one. If I divide it, K become here, A become here, this represent my M. And this might represent my theta. And if we take the derivative, the same as this one, okay? Therefore, there is nothing strange here, okay? If I take the second derivative from here, this disappear, because this is constant, okay? It's constant, disappear, and that's the theta. And here is my M here. You know better than me, the general solution is becoming this form. It's your mathematics that you have, okay? Therefore, this is the general solution. We have e to mx, e to minus mx. Therefore, our responsibility here is trying to define our application, our scenario based on the boundary condition to be able to solve this differential equation and trying to find the value of C1 and C2, okay? Trying to find this one and this one. Therefore, we need two boundary conditions to do that, okay? This does not make sense, okay? Therefore, we're trying to find what it is. What makes sense for our application. Therefore, C1 and C2 are constant whose value are to be determined from the boundary condition that we have. We always have one boundary condition because at x equals 0, we know the temperature. Okay, that x equals 0 becomes the temperature, okay? We know this one. The second boundary condition is at x equals L. Again, depend on your design. Under your design, you can specify temperature. Probably this side will be exposed to a scenario that the temperature we know that, for example, is 40 degrees. Okay, it's fixed. Or we can assume that it's too long, the fin is too long, therefore we can assume the temperature here is infinity. We can assume negligible heat loss from here. We can assume this is a scenario that is heat loss is almost 0. And that could be the case between that you have a fin between two surfaces. One surface is here and usual design of heat exchanger, and you have another case here, T0 here. Therefore, we can assume this is the scenario. In another case, we assume that you have a convective heat loss from here. You can have it. You can have convective. Therefore, based on this scenario that you may have, you can have different solutions to this problem that you have. Therefore, every time you have to solve this problem based on the boundary condition that you have, and you will end up different value for C1 and C2, okay? Depend on the assumption that you make, you have different solution to this problem, okay? Again, just look at this differential equation. You do not need to memorize, you do not need to do anything, just familiarize with the format, okay? Because you have the solution to this from your textbook. The only thing just to learn the assumptions are made for each scenario, okay? Therefore, this is only one sample of assumption. We can have different design and different scenario. Therefore, if we can say specify temperature, therefore the boundary condition expressed here is this at 0. You know, this is TB equal minus this one. Again, this is the temperature of the base is given to you, minus infinity. Therefore, we can solve this differential equation and based on different force scenario that you have, okay? Infinity long, adiabatic, it means losses is negligible, convective here. Therefore, you have at least in your textbook for the 4 different scenarios, and they solved this 4 different scenarios, and they came up with a solution. For example, okay, if you assume the fin is too long, it means the temperature here is the same as in temperature outside, okay, T infinity. Therefore, they solve this differential equation, and your text would mention, and the answer becomes Tx. That means temperature at every point along the pipe, along the fin, and temperature along anything, minus T infinity. This is the temperature of the base. You know what is the base of your fin? Okay, if you not, this is the color temperature of the base. Okay, this is the wall that fin is added. This temperature usually we can calculate. Let's see. Therefore, you can see the temperature drop slowly, exponentially, and therefore from you have this equation. If you know the convectivity transfer, if you know the size of the fin, if you know the conductivity, you can calculate the temperature at any point. Okay, you can calculate the temperature profile from here to here. Therefore, this solution is given to you, and you have the solution in your textbook. Therefore, the only thing we would like to know that you trying to understand the procedure. Okay, the procedure, how you, what assumption that you make, and what was the technique that you use trying to solve the differential equation. And now we would like to see if this is your fin here, how much is heat loss to this fin, As I mentioned, this could be cylindrical, it could be rectangular. If we were trying to find how much heat loss in this case, in this scenario, that is too long. Therefore, the temperature here is T infinity. Therefore, you place it here is K, A, dt or dt. You have expression here of the temperature that gave you the temperature profile along the fin here. And if you calculate the value of dt over dx at this point, you have this temperature profile, dt over dx. If you take the derivative of this equation, and put it in this expression here, you will end up with this one, okay? And for now, you can have an expression to calculate the heat loss from the fin. You can also calculate the heat loss from the base, and that's the total heat loss from that wall, okay? Therefore, this equation is only tell you how much energy loss from this fin here, okay? But also you have base. You can use the conventional technique to calculate this one. Any question, please? Any question, please? Don't be shy. We have still a few minutes left. I can go back and explain. The question I would like to understand why we use the fin, what is the fundamental behind that, and what is the procedure we're trying to develop the equation, okay?
I have a question, Professor.
Yes, sir.
Could you go back 2 slides, please?
Yeah,
How does, can you go forward 1 more slide?
back or forth?
Forward, please.
This one?
Yes, how does, could you explain how exactly equation 3-56 relates to the fin equation that we went over previously?
Yeah, you see, you have this equation here. And in order to make it in general form of the equation, okay? As I mentioned, K is constant comes out. You agree? AC constant comes out. And you divide this side equation by K over AC. Therefore, this will cancel out and come over here. Become HP divided by K AC. You agree with me, sir?
Yes.
Okay, therefore I call this one M. HP over KA, we call them M. Now, in order for us to be able to visually understand the equation, here you have T minus T infinity. Here you have T. One way we did it in mathematics, we change of the variable. I call T minus T infinity equal theta. I just use a new variable. I don't like T, I call it theta. Therefore, I call it T minus infinity. This expression, I call it theta. Therefore, this becomes HP over KAC times theta. Now, remember, T infinity is constant. If I take the derivative of T minus T infinity, becomes dt over dx. Because this is constant, becomes 0. The derivative of the constant is equal to 0. If I get the second derivative, become this one. Therefore, this expression comes here. This was my HP over KC. I call it M2. I call T minus T infinity theta. Okay. Now, if I take the derivative from both sides of this equation, this becomes d theta over dx, becomes dt over dx, and this becomes 0 because this is constant. The derivative of the constant is 0. Therefore, becomes d theta over dx, dt over dx. Okay, take the second derivative become. Therefore, this is, we call it change of the variable. We just change the variable to make the equation look nicer. It's easier to solve. Okay, that's exactly the procedure that you had it in your Math 233. Okay. Therefore, and if you remember the Math 233, when we have equation like this, the general solution, we call it the general solution, is in this format. Sometimes this equals 0, sometimes this equals 0. In general solution is like this. I do not know which format it is at this moment. This is a general format. And I apply it to my scenario for the case that I have. Okay, for this scenario that I have, okay? And try to see which one will satisfy. If I look at, for example, in this case, you can see the positive disappear as only mx negative here, okay? Therefore, depend on scenario, Probably C2 is equal 0, C1 is equal 0, and I have only C2, okay? Therefore, that's why we have, for different application, different boundary condition, and based on those boundary condition, if I can go back and solve this differential equation, I get different answer. And if you look at your textbook, you have a table that shows you different. Let me go further. I believe I have to copy here. If I assume, again, the same equation and try to solve it is adiabatic, it means, okay, let me go back. Did I answer to your question first, sir, before I go further?
Yes, you did.
Therefore, put it in your paper here and to see what will happen. Assume dt t minus t infinity is equal to theta. Take first derivative and second derivative. You will see that the equation will transfer to this one. This is a general equation, and that's fine. Okay. Let me see. I have 2 minutes. Do you have any question about your project? Let me stop here. Answer your question if you have any question about your project.
Hi, Professor. Can we assume that computers, after they close, they don't generate heat anymore?
Your computer does not generate any heat?
Yeah, I mean, like when they're closed, they don't generate heat anymore.
Yeah, you can say that the computer is off. Okay. There's, as again, this comes as part of assumption. Probably your computer doesn't work. You turn it off during the night. Somebody probably doing some simulation, and he or she would like the computer on during night. These are the assumptions that you make. That's exactly happened in real scenario. Every problem has a different scenario, and we have to solve that problem for that scenario. Okay, but we can assume that you finish your job, your computer is off, and therefore you put it off. Somebody else says, well, no, I need to keep it on because I'm doing some simulation and the computer has to run, or I'm getting a message from different people I would like to track it. Again, these are the assumptions that you have to clarify in your report. Okay. Any other question?
I have one more question.
Yes, sir.
For the objective of the first part of the project, when it says to determine the temperature distributions in the northeast and south walls, are you asking specifically what the temperature on each of those 3 walls is?
No, what I would like, as I mentioned, I would like that you be able to visualize what exactly happened in 24 hours. I would like you to draw the temperature on each layer of the wall as a function of the time. 24 hours, I would like to find out what is the temperature profile for exterior surface, what is the temperature at 10 centimeter inside. Therefore, this will help you have much better understanding of the physics of the problem, okay? Because you look at the problem, you get the answer, then you use your judgment and say, okay, could the temperature at point 2 be more than 0.1? Probably a computer simulation give you that one. Probably is correct, probably wrong, because I would like you to be able to visualize your answer and trying to make a judgment and trying to explain why this is happening. It could be correct, it could be not correct, depend on assumption that you're making. That's why I mentioned, specify what assumption that you would like to have, okay? Specify that assumption, I look at your assumption, I look at your solution and say, well, your answer is correct. But if you make an assumption, but your result does not match the assumption, that's wrong, okay? Therefore, its visualization is important for us as engineers to see what's exactly happening. And the second part is much, much better because then you will see something strange will happen, okay? The first part is the steady state. The temperature inside the room is changing as a function of time. The temperature outside changing. How will happen in between inside and outside, between a different layer of the wall, okay? Therefore, I want you to have a graph, time, 24 hours, the temperature, and different line for different layer, okay?
Sir, to my understanding is we analyze each wall for different layers.
No. You're in a house, sir. You're in a room. Therefore, you have to do it simultaneously, all of them the same time, sir. You cannot write one set of equation for each wall and solve them independently. east and west, south, they are integrated together because they are linking the room together.
Right. So you were saying you look for the temperature distribution on each wall, right?
That's right. When you solve those harmonic equation unknown that you have, it gave you the temperature at every point for each wall. And I would like you to write, for example, for 2 walls or 3 walls and explain it, your result. Because we have to start to be able to judge the result. Tomorrow you become engineer, you use any simulation and you get the result. And if your result does not make sense, you will be sued and you lose everything, my friend. You are a professional engineer, you are responsible to make judgment. You cannot say, well, I use this simulation tool and got this result. You have to use your judgment.
Okay, so how would you like us to select the points on the wall?
You select it and you explain it to me, my friend.
Okay, okay.
Then select it every 5 centimeters, select it every 10 centimeters, okay? Again, this is the problem. Each of you use your own judgment, okay? That's why I mentioned probably I have 75 problem and 75 different answer. I don't expect your answer is the same as somebody else. That's exactly real life scenario. Based on assumption that you are making, you will get different answer, my friend.
The heat generation from infiltration is also includes other variable like Q. Is it possible?
Well, there's no heat generation by infiltration.
Yeah, it's varying. It's varying from depending on the temperature inside and temperature outside. So it should be an equation.
Energy exchange. There's no heat generation. There's energy exchange between inside and outside, and that's due to the infiltration. If you're taking air, your building is leaky, bring some air from outside to inside. Therefore, there is some energy exchange between inside and outside, and that's the case, yes.
Okay, thank you.
No problem. Any other question? Again, thank you very much. I believe now some of you have a tutorial, right? There's a tutorial today?
Yeah, we do have tutorial, but just one last question. So when we do the
Before you ask me a question, I would ask, since most of you are still on the system, please do attend the tutorial because the tutor is trying to arrange some office hours in case if you need some help. Therefore, if you are there, you can tell him this time is good or bad for you. Talk, communicate, don't sit quiet there because I asked him to discuss it with you and to see what time is the best for you that you can approach him or that. Therefore, he's trying to give you some suggestion. Make sure that is match your time, free time, okay? It's not exactly time, okay? Therefore, he cannot satisfy all of you. Probably he can satisfy, I asked him to give you 2 times that at least will satisfy everybody, okay? Please attend and please talk. Don't fall asleep as you're falling right now. Yes, dear. Now, ask your question, Mr. Wu.
Yes. So are we analyzing the point in terms of layers or on the surface of the walls?
My friend, as I mentioned here, is I would like to look at the temperature at different point on the surface inside the wall at 1 or 2, 3 points that you would like.
Oh, okay, okay. So everything.
That's right. I would like you to see the temperature distribution inside the wall.
Okay, okay.
Temperature distribution in the wall, it means you get 3 slices, 4 slices, and one is exterior, one 5 centimeter, 10 centimeter, 15 centimeter, and so on. Okay, whatever you select. Okay, at least minimum 2 points.
Okay, perfect. Thank you, sir.
No problem, sir. Any other question? Thank you very much for your time. Please go to tutorial and also do attend the other group attend tomorrow. Please, at least during the tutorial, discuss it to find the best time that we will be able to help you, okay? Have a nice evening. If you are finished, done, and if you have any question, I will be still on the system. Adios.
Thank you, sir. Have a good evening.
You too there. Bye-bye. Again, I forgot to ask this. actually person to discuss about the memory I have.